So can people see my screen?
Yes.
Okay, good. So I will do the introduction to HPC2N, Kebnekaise, and HPC. So HPC2N is short for High Performance Computing Center North, and it's what we call a competence center for scientific and parallel computing. And we are part of NICE, which is the new name for what was previously SNIC. So it's National Academic Infrastructure for Supercomputing in Sweden. And what is HPC2N? Well, we provide state-of-the-art resources and expertise. That is, we have scalable and parallel HPC, and that is currently in the form of Kebnekaise. We have large-scale storage facilities. We have the Luster system, which has the project storage. And you currently have some storage on that because there is one for the course project. We help out with space for the Swiss store, and we have tape storage as well. We are part of grid and cloud computing. We have a small cloud system, and this should not have said SNIC here. It should have said Sweden Science Cloud, which is now the name for it. So I will fix that. I overlooked that when I fixed my slides. And for grid computing, there's a WLCG that we are known for, and WLCG, that is compute and storage for the Large Hadron Collider down in CERN. So we provide some for them. And then we are also now a national data science node in the epidemiology and biology of infections, that is the DDLS, and that is together with SciLife Lab. And we provide software for e-science applications. In addition to that, we have all levels of user support. So there's primary support, advanced support, dedicated support, where we can help a research group directly. And there is a number of application experts which handles most of those types of support. So HPC2N's primary objective is to raise the national and local level of HPC competence and transfer HPC knowledge and technology to new users in academia and industry. And HPC2N is hosted by Umeå University, and we have some partners which are the IRF, that is Space Physics up in Kiruna, and that is Luleå Technical University. There is the Mid University, which is in Sundsvall, and then there's SLU, which is also here in Umeå, at least part of it is. We are funded mainly by Umeå University, and we get some contribution from the other HPC2N partners. And then we're involved in several projects and collaborations. So as I said, we have user support, and we also do some research group meetings at Umeå. So if you are in a research group, we may call you to meetings now and then to see if there is some special need you have, or you can contact us and say if there's something you need help with. And we also do that at the partner sites. Then we have our user training and education program. And that is, for instance, this intro course, but we also have a great number of other courses. As you can see here is a list of the most recent courses, which is aside from this intro course. There is a MATLAB workshop, which is running next week, which we are involved in. And then there is the introduction to running R, Python, and Julia. That is still open for registration, so you can sign up for that if you want to. Then we will have an introduction to Git, and that will be in November. And we have not opened the registrations for that yet, but that will happen probably within the next few weeks. And then there will be a course that focuses more on using Python in an HPC environment. So it is not for people who don't know Python, it's for someone who actually knows Python but wants to know how to use it better in an HPC environment, what extra ways there is to do that, things like this. Aside from that, we have some workshops and seminars from time to time, and some of those has been recorded, and you can generally find recordings from courses and seminars that HPC2N is involved in on our YouTube channel. And we also take part of some university courses that are held at our systems. So what are our personnel? Currently, our director is Paolo Biantinesi, and we have a deputy director, Björn Torkelsson, and Lena Hellman is the administrator. Then we have some application experts, and officially it's Jerry and Pedro. And we also have other people. There are some people involved with the various projects that we're involved in. And then there's system and support. And on the system and support, I have bolded some people which are also doing application experts, also being application experts, even though not to a lesser degree, I guess you could say. And the Jerry is specializing in these areas that I show here, and Pedro in these, mainly molecular dynamics and profiling, and also Gaussian and R, and also other things. We are all also general, but we have some special areas. So, and to contact us, you do that through the regular support. You can say that you would like to talk to an application expert, or you can just ask a question through the HPC2N support. And then if it's something that takes a bit more time or falls on the special area for one of the application experts, then you would be assigned help from that person. So HPC2N, what kind of users do we have? We have a very wide range of users, as you can see. There is bioscience and medicine and chemistry, computing science, physics, mathematics, all kinds of things, but not a lot in the humanistics, and that is something we are hoping to get more users from as well. So, and this is a growing area, of course, AI and everything under that. So these are several scientific disciplines which has the largest users, and chemistry, material science, and physics are probably the biggest ones, though machine learning in all areas is growing. And here you can see a chart that shows the core hour uses per software for Kebnekaise. And under the unclassified thing is things that people are either running directly on the node or things that, for instance, code they have developed themselves will be under that as well, and that will be much of it. But you can see that which types of software is popular, and you can see something like CP2K and GrowMax are popular. The Atlas is actually for the VLCG grid computing. So that is the one from CERN. So Kebnekaise, that is our current supercomputing computer, and it's a name for a massif which contains some of Sweden's highest mountain peaks, and you can find that on the map. It's to the north. And it was delivered by Lenovo. We got it in 2016, and it was opened for availability in the late fall of 2016. Then we got it extended in 2018, updated with some Skylake nodes and some Volta V100 NVIDIA GPU nodes. And then again this year, we have started to get A100 nodes, GPU nodes, and we will get more new hardware over time now. So what do we have? We have the compute nodes, and it's these. And as you can see, I've written here the Intel Xeon E5 nodes here. That is the Broadwell nodes, these that we have a lot of. They will slowly be phased out. And currently many of them are turned off, but they can be turned on if there's a use for them. And we will get newer hardware over time as well. So And there is still the large memory node, which will not be phased out because people have a use for that. Then we have GPU nodes, and there is the new A100s. And as you can see, it has both CUDA and Tensor cores. And then there is the Volta nodes, which are also still running. And then we have two groups of K80 nodes, which are located on the Broadwell nodes, and those will be phased out. And the main reason for that is that they cannot run newer versions of CUDA. And that means that we cannot update, at least not easily update, the rest of our GPU nodes to the newer versions of CUDA unless we turn off these K80s. Otherwise, we would have to split it up into several systems, and that would be a lot of work. So these will be phased out, and also it is better to use the newer hardware for many other reasons. And we will, as I said, get more of them. So in numbers, we have 15 racks with 553 nodes, if we count all of it. And we have Broadwell, Skylake, and AMD Zen 3 nodes. We have NVIDIA A100, B100, and K80 GPUs. And there's more than 135 terabytes of memory. There's also a lot of switches, which are both the access and management network, but also InfiniBand for communication between the nodes and inside of the nodes. Inside of the racks, sorry. And this is just counted together how many CPU nodes, CPU cores, CUDA cores, and Tensor cores there are. So as you can see, it's quite a lot. So Kebnekaise also has, HPC2N also has storage, and there are 4 types of storage. We have the home directory, which is where you end up when you log into the system. There's 25 gigabytes there. It's not a lot, so it's just meant for whatever files and mainly setup and configuration files that you want backed up and you want saved. Then there's project storage, and this is where you will be running usually your jobs. And that is, there will be some with the project. When you apply for compute project, you can get 500 gigabytes of project storage as default. Or you can say that you don't want that and that you will instead apply for storage project directly, and then you can get significantly more. In any case, this is where you will be running your jobs, and it will be shared among project members. So in this case, we have a storage project together with the compute project, and under that, I wrote in the email to you that you should create a directory for yourself so that it doesn't get mingled together with everyone else. If everyone is running in the same directory, it will be chaos. So just create your own one under the project storage. And I can log into Kebnekaise and show you where it is. It's here. And I choose to use the same name as the name for the compute project because it's easier to remember that way. So you can go to this directory here. And when you're there, you can see that I have what is called a tarball that Pedro talked about earlier. And that contains the material for the course. And you can also get it from Git. And there are 2 people who have created directories, and I'm going to create one as well, like this, mkdir, and then the name I pick for myself, and I'm using my username because that makes it easy for me to remember. So I can go into that, and now I have a space here where I can work with the exercises text, and I will show you in a little while how to clone it from Git. So aside from these two types of storage, there is also what is called local scratch space that will be on each node. And that is what we call volatile. That means it's only yours during the run. So when a job finishes, you will have to make sure that everything you had in it are copied to a place where it will stay. I mean, that will happen automatically unless you directly do something in your job to run there. But otherwise, it is accessible during the run of the job only. We also have tape storage that is used for backup and long-term storage. It is not directly accessible by the users, but your home directories will be backed up to this, and that is the safe space for it, so that it can be retrieved from there if something happens. So, and we also do storage for some other departments and some other places in Sweden in this tape storage. So there are backups in different places in the country often. And then there's something called Svestore, which is disk-based, and that is used for research data storage infrastructure, and that is for active research data. It's operated by NICE, and you apply for that through Super. So, as I mentioned before, there are some projects. We have a project, and to use it, Kebnekaise or any other system in Sweden, in general, you must be a member of a compute project. It has some core hours, and in this case, we have what is called a small local project on Kebnekaise. And you can see that with Proi info, or you can go to Super and look at it. But you can see here, if I say Proi info, it will show this project here, but also any other projects you have. So since I am in several projects, including sysop projects, then it will take a while to list. So it's easiest for you to, if you're only in one project, you can just say Proi info. Otherwise, you would say Proi info minus P and then the ID for the project, which in this case is the HPC2N 2023 minus 102. So a regular CPU core, it costs 1 core hour per hour. Other resources like the GPUs cost more, and that is listed on our website. And I will also look at it some in the next session. It's not a hard limit, which is important to remember. So even if you only have, say, 5,000 core hours per month, you can still use 7,000. There's nothing stopping you, but your allocation will get lower priority. So if many people are running and they have higher priority, their jobs will start before yours. And then slowly you will regain priority and your jobs will start faster. And this compute project, it can contain amount of storage. If you need more, you have to have a storage project, which you also apply for through Super, just like you do with the compute project. And since Kebnekaise is now a local cluster, you need to be affiliated with either Umeå or one of the partner sites to use it. And as I said, projects applied for through Super, and you have all seen Super because you all got an account there and sign their user agreement and things so that they are happy and that we can give them user accounts. So I will look at that in next session. So just quickly, what is HPC? And I will skip this definition since we are short of time. And let's see, you can see here, we can, it's aggregating computing power in HPC. We have a lot of nodes, we have a lot of cores. And if you compare that to 4 cores in a modern laptop, maybe a little more, this is a lot more cores. So that is one reason why you might want to use HPC instead. And because there are more cores and the nodes are possibly faster, then it will have many more arithmetic operations per second than, for instance, a laptop does. So that is the idea with HPC, that is that you want to solve large problems on it. It's not for something small that will easily run on your laptop, it's for something big, either in terms of memory or in terms of more cores, faster cores, or you need software support or other things. It might be that you don't have a license for software that we have, or in many cases you need a license for the software anyway, but some of them we will have, some of it we can install. So there are many reasons for it. So a problem can be large for two main reasons. There is the execution time. It could be that it takes very long to solve the problem, or it could be that it requires a lot of memory and or storage. And you can remedy the execution time by increasing the performance, by giving more cores, more nodes, GPUs, faster nodes, etc. And if you need more memory or storage, you can add more memory or storage. Kebnekaise has quite a lot of memory. As you can see, that is between 128 and 192 gigabytes. All the newer ones have 192. And there is the large memory nodes, if you really need a lot of memory, that have 3 terabytes. And it's also possible to get more storage. So I have this, picture here. So HPC is not what you run on laptops or big workstations. It's what's needed for a small computing cluster or for a supercomputer. So we also have some specialized hardware, as I said. These GPUs we have are optimized for AI, but they're also good for many other things. Many pieces of software like GROMACS and other things are compiled, so it will run well on the GPUs. We have high-end CPUs. We have some good memory that are error correcting. And we hold licenses for several types of software. And not unimportantly, we have pre-configured it and made it ready to use, so you don't need to spend time on doing that. We also have support that can help you, and we already have pre-written some documentation. So there are 2 types of memory models that are relevant for HPC. You have the shared memory and you have the distributed memory. The shared memories would be when you are running inside of a node usually, and that is something that you would, for instance, use OpenMP to handle. The distributed memory, you would use something like MPI, and that is if you're running on many nodes, for instance, because that is the multiple distinct memory spaces. And again, shared memory is what you have on your laptop, on your workstation, and it's also what is within a compute node. But as soon as you go out to something across several nodes, if it's a bigger problem that you need to run on, then you have to have distributed memory because each of the nodes have their own block of memory or within GPUs. So the programming model changes. If we want extra performance of memory, you can have just single core. Many people run single core jobs, but run a lot of them, for instance, like MATLAB, Python, C, Fortran, or you can run multi-core jobs. And that is, for instance, if you're staying within the number of cores that is on one nodes, then it might be something like vectorized MATLAB, OpenMP. And if it's distributed memory, if you need even more cores, then you would need to use something like MPI or a program that is using MPI or other types of distributed memory, because many software types already have that built in. And there's also GPUs where you could maybe have written it in CUDA, or you could use OpenMP, OpenACC, OpenCL, or software that already is written for it. And that is many lightweight streams of operations. And within GPUs, that is data distribution across memory spaces and movements. So if you're doing it yourself, you handle that, but usually many of our users will be using programs that already are compiled or written to use this. So, and the complexity grows when we aim for extra performance. For instance, if you're just using single core, maybe you use LAPAC. If you are using multi-core, then you also need to add something like parallel BLAS. And you need to think about not just which toolchain to use, but also the number of cores. If you're using distributed memory and something you've written yourself, maybe you're using scalar pack. And you need to take care of data distribution also. And then also, if it's GPUs, you need to get the correct number of cores and or GPUs and things like this. So I went through this little bit faster than I wanted to, but we are out of time. So, but we can take a few questions if anyone have. Here you go. Now, do you see them?
Yes.
Good.
Yeah, we see it now.
Good. Okay. So I am going to share this link again to you here, but otherwise it's in the important info and also in the email. But if you go to this GitHub page and you can go into this directory that's called hands-ons. And then under that, go to section 2. And here is the exercise, or what to call it, for how to connect to HPC2N systems. And in order to do that, you should either use whatever SSH client you have, or if you don't have one, then use ThinLink. And that is actually probably the most recommended one, for the simple reason that you will then also get a graphical interface. And that is something that you will use for some of the exercises for the application part that will be in the afternoon. So what you can do is you can go to this link here and download the client, or you can use it through the web access desktop here. This one, the web access desktop, has fewer features. It's a little bit more difficult to copy things to it, though it's possible. But if you can, I would suggest downloading this client. It's very simple. You just download it and start it up. And we have some extra documentation here about how to use it, but it's mainly, I can open this here. Because what is important is that when you have downloaded and started it up, then you will get something that looks like this here. And you will log into Kebnekaise -tl.hpc2n.umu.se. And then you put your username. And you should also do some setup to it first. So what you should do is click Advanced. And then under that, go to Options Security, make sure it's set to password. Go to Display and mark Windowed. And that is important because if you don't, it may flow larger than what will fit on a laptop window, for instance, if you're using that. And if there should be anything on the local devices, you can uncheck sounds and things like that there, but there's likely not anything there. Then you should enter your HPC2N password, and it's important that it is entered here, because otherwise it will ask for it, but it will fail. So it needs to be put here on this window. And then you click Connect, and you will be asked if you want to put the server's host key in the registry, because it's not there yet, and you just say Continue. And then it will be a few minutes or so the first time. Then the desktop for ThinLink will open running mate, and it will look much like a regular Linux GNOME desktop. And you will be able to get all your files that are on HPC2N there. But of course, on your own machines, you will have to copy there. So if you haven't tried to log into HPC2N before, you will maybe wonder where your password is. And in the email you got when you were told that your account had been created, there would have been a link to a page, and it will be this page here. See, it's the same as you would use for forgotten password. You will get it here because there's a password reset page service here, and it looks like this. And this link here, that's up here, the URL here, that will be in your email, but I will also put it in the chat. And when you, I'm just answering this here to someone. I sent the link here in the chat. And to do that, you will simply click Authenticate in Super. And what you do there is that you will be taken to a Super page, and there you will write your Super username and password, or however else you will log into Super, and then you will say, yes, I authenticate. And then you will be given a page that contains a temporary password. And this password you will put in to here. And I strongly suggest that you change this password immediately after logging in. And you do, let's probably show it here. You do that with the command that looks like this, passwd. So you write that on the terminal, and then you click enter. It will ask for your old password. That is where you put the temporary password you just got, and click enter. It will then ask you for a new password. Create one that you can remember. Click enter, and then write the new password one more time. It will then have been changed. So the next time you log in, you will use the new password.